Welcome back, everyone. Up to now, we have spent 14 lectures immersed in the world of infrared spectroscopy. We explored molecular vibrations, infrared absorption, group frequencies, fractal transitions, FTIR instrumentation, sample preparation, and sample spectral interpretation. Throughout all of these discussions, one fundamental idea remained constant, that is, molecules absorb light. But today we are going to talk about or going to explore a completely different interaction between light and matter. Today we move from absorption to scattering. Welcome to the fascinating world of Raman spectroscopy. At a first glance, Raman spectroscopy may seem similar to IR spectroscopy. Both techniques provide information about molecular vibrations, bond strains, and molecular structure, but the physical mechanism is entirely different. IR spectroscopy measures the absorption of light, Raman spectroscopy measures the scattering of light, and that distinction changes everything. Whenever electromagnetic radiation passes through a transparent material, several things can happen. Some light may be absorbed, transmitted, reflected, or scattered. Most of the scattered light emerges with exactly the same wavelength as the incident light. This is called elastic scattering. But a tiny fraction of scattered light changes its energy during the interaction. This energy shift correspond directly to molecular vibrational energies. That phenomena is Raman scattering. So let us now examine the origin of Raman scattering more carefully. Suppose we shine monochromatic light into a molecule, most photons scatter without changing energy. The ongoing photon has exactly the same frequency as the incoming photon. This process is called Rayleigh scattering. Rayleigh scattering is overwhelming dominant. In fact, Raman scattering is extremely weak, typically only about 1 in every 10 million photons undergoes Raman scattering. In Raman scattering, the molecule exchanges vibrational energy with the photon. As a result, the scattered photon emerges with a slightly different energy. That tiny energy difference gives us vibrational information. Now here is extremely important point. Not all molecular vibrations are visible in IR spectroscopy, not all visible in Raman spectroscopy. The two techniques obey different quantum mechanical selection rules. For a vibration to be IR active, it must involve a change in dipole moment. For vibration to be Raman active, it must involve a change in polarability. This means some vibrational modes in invisible IR becomes highly visible in Raman and vice versa. Raman spectroscopy also provides enormous practical advantages. As we discussed previously, water is a nightmare in IR spectroscopy. Water absorbs IR radiation very strongly. This creates major problems for aqueous samples. But in Raman spectroscopy, water is a very big scatterer. That means we can easily study aqueous solutions, proteins, biological tissues, inorganic ions, and living systems. And unlike IR spectroscopy, Raman measurement can often be performed directly in ordinary glass containers. No salt plates are required. Because of these advantages, Raman spectroscopy is widely used in pharmaceutical analysis, nanotechnology, biochemistry, material science, and many more fields. Now, let us briefly examine the historical moment. Raman spectroscopy was discovered by Sir C.V. Raman in 1928. He demonstrated experimentally that scattered light could change wavelength depending on the molecular structure. This was revolutionary discovery in molecular physics. For this work, Raman received Nobel Prize in Physics, making him one of the most important physicists in the history of spectroscopy. Although Raman discovered the effect in 1928, the technique remained difficult for decades. Why? because the Raman scattering is incredibly weak. Early light sources simply were not intense enough. But everything changed in 1960s with the invention of the laser. Lasers provided high intensity monochromaticity, coherence, and stability. Exactly what Raman spectroscopy needed. Modern Raman spectroscopy becomes practical only because of laser technology. Now let us examine the actual energy exchange process. This is one of the most important concepts in Raman spectroscopy. Suppose we illuminate a molecule using a monochromatic laser. The incoming photons possess energy E is equal to h nu, where h is the Planck's constant, nu is the excitation frequency. When a photon interacts with the molecule is briefly distorted into a temporary state called a virtual state. A virtual state is not a real quantized electronic energy level, it is a temporary distortion of an electron cloud. The molecule exists in this state for an incredibly short time, typically femtosecond. It immediately relaxes and re-emits a photon. First, consider the simplest case. The molecule starts in nu is equal to 0, enters the virtual state and returns back to nu is equal to 0. No vibrational energy changes. Therefore, the emitted photon has exactly the same energy as the incident photon. This is Rayleigh scattering, it is an elastic scattering process. Now let us examine the more interesting case. Suppose the molecule begins in nu is equal to 0, enters in virtual state, but relaxes into nu is equal to 1. The molecule gains vibrational energy. That energy must come from the photon. So the scattered photon loses energy. Lower photon energy means lower frequency, and the longer wavelength, this produces the Stokes lines. Now consider the opposite situation. Suppose the thermal energy already placed in the molecule in nu is equal to 1. The molecule absorbs energy into the virtual state and then relaxes down to nu is equal to 0. Now the molecule gives excess vibrational energy back to the photon. The scattered photon emerges with high energy, higher frequency and shorter wavelength. This produces the anti-Stokes line. Now let us examine the actual Raman spectrum. Notice the enormous central peak, that is the Rayleigh line. It dominates the spectrum because elastic scattering is overwhelmingly more probable. Now observe the weaker peaks on either side. The Stokes lines appear on one side, the anti-Stokes lines appear on the other side. At room temperature, most molecules occupy vibrational ground state, nu is equal to 0. Very few occupy excited states like nu is equal to 1. Therefore, Stokes transitions originating from nu is equal to 0 occur much more frequently than anti-Stokes transitions originating from nu is equal to 1. As a result, Stokes lines are stronger than anti-Stokes lines. Interestingly, the anti-Stokes intensity increases with the temperature. Why? Because higher temperature populate higher vibrational states more strongly. This allows Raman spectroscopy to estimate molecular temperature in some systems. Now, let us unify everything with the energy level diagram. The Raman shift equals vibrational energy difference delta E between molecular vibrational states. For Stokes scattering, E is equal to h nu minus delta E. The scattered photon loses energy. For anti-Stokes scattering, E is equal to h nu plus delta E. The scattered photons gains energy. Notice something remarkable. The vibrational energy spacing measured in Raman spectroscopy is identical to the vibrational spacing measured in infrared spectroscopy. The molecular vibrations themselves are the same, only the interaction mechanism differs. In Raman spectroscopy, we rarely focus on absolute photon energy. Instead, we focus on Raman shift, usually measured in centimeter inverse. The Raman shift directly corresponding to molecular vibrational frequencies, making interpretation intuitive and comparable to IR spectroscopy. Let us summarize today's lecture, in which we have learned Raman spectroscopy measures inelastic scattering of light. Most scattered light undergoes Rayleigh scattering, but a tiny fraction undergoes Raman scattering. We explored virtual states, Stokes scattering, anti-Stokes scattering, and the Raman shift. We also learned why the Raman spectroscopy is complementary to IR spectroscopy and especially useful for aqueous and biological samples. In our next lecture, we will dive deeper into mathematical origin of Raman intensity. We will introduce one of the most important concept in Raman theory, that is polarizability, and we will finally understand why some vibrations are Raman active while others are completely silent. Thank you for watching, and I will see you in the next lecture.